Hi there, Mr. Sutton here, bringing you this lesson on triangle area. In this one, we are going to find the area of a triangle if we have three sides, or if we have two sides and the angle between them. For a real-life application, one of them anyway, we're going to find the area of a non-right triangle-shaped piece of land. We're going to start this lesson off by just laying it all out there. So down below here are three big situations where we would need to find the triangle area, which we'll refer to as either A or K, depending on whether we're trying to avoid confusion with letters that are already out there. So the common case that you're already used to is when you have the base and the height of a right triangle, and then you can just do a 1/2 base times height to get the area, which we call A in the old geometry formula here. So that works great if you can find the height, but what if you can't? What if you have this situation over here? And let's go a little further, because we've done triangles like this where we were able to get the height. Let's say that we can't get the height based off of what they gave us. Let's say that we have instead three sides of a non-right triangle, or maybe it's a right triangle, but it doesn't matter because we can't find the height. So in this situation, we're going to actually take a two-step approach. Our first step is we're going to find the semi-perimeter, which I'm going to call little s, and the semi-perimeter is just what it sounds like. It's half the perimeter. So you just add up the three sides, A plus B plus C, and take half of that. And that's your S value. Now, once you've got this S value, what do you do with it? Well, here's the actual area formula in this situation, and we're going to use a K just so we avoid confusion with the A that's already in there. We're going to say K equals, and this is going to be a huge square root now, S times S minus A times S minus B times, you want to guess what the next one is? Yep, S minus C. So you multiply the semi-perimeter times the semi-perimeter's difference with the three sides. And this is a long formula, but it does the job. And this actually has a name. This is actually called Heron's formula, or sometimes Hero's formula. So the last situation we're going to deal with, what if we have two sides and an angle between them? Side, angle, side. So in this situation, we have another formula, which is going to be called the Half-Sine Formula. We're going to say K equals 1/2. And now this is actually going to be kind of similar to this right triangle formula. We're going to have A times B times the sine of the angle between them, the sine of C. And again, this is the Half-Sine Formula. So there's a link to a proof of Heron's formula to show that it works. And we'll actually go over a little mini proof of the Half-Sine Formula at the end of this lesson. But before then, we're actually just going to get some practice using these. Let's begin now by getting a little practice with Heron's formula. Now, we know we need Heron's in this one because we've got three sides. So I recommend you start by writing down both parts of this formula. So let's start with our semi-perimeter, 1/2 times A plus B plus C. And the nice thing about this formula is that you don't have to worry too much about what is A and B and C. It's not like the Pythagorean theorem where C has to be the hypotenuse, because there is no hypotenuse. It's not necessarily a right triangle. So since you're adding them, A, B, and C, just pick whatever numbers you want as long as they're sides of the triangle. So I'm going to go with 25 plus 13 plus 20 in that order. But again, the order doesn't really matter. And now, let me just crunch this on the calculator. I could do this without one, but we're going to end up using the calculator later on anyway. So let's just start now. So here we go, crunching those numbers, finding my semi-perimeter, which is 29. Okay. So now that I found S, let me write out my general area formula for Heron's. That was the square root of S times S minus A, S minus B, S minus C. And then let's plug in all of these things here. So we've got a square root, and again, S was 29. S minus A, that's going to be 29 minus one of these sides, and might as well just keep the order that we used before. So we'll say 29 minus 25, because that's what I chose for A. And then S minus B, let's use 29 minus 13. And then S minus C, we'll use 29 minus 20. And let's just plug all this in the calculator. Now, you could do this in different steps. I mean, you could call this 4 and 16 and 9. But I really just highly recommend you plug it all into the calculator at once, because you're going to have to anyway. So let's do let the calculator do the heavy lifting and all the PEMDAS. So I've taken a moment off camera to plug all that in my calculator. That's the end of the square root bar. Pressing enter, looks like we've got 129.2 if we round off to the nearest tenth. So even though Heron's takes a while, you might be thinking it's a pretty useful formula, because in terms of what you can do in real life, you're probably most likely to be able to get the three sides of a triangle measured out in a real situation. But there are times when it's hard to get that third side. Take a look at this problem, for example. Let's say you own a triangular-shaped piece of land bounded by two roads. So there's one, there's two, and we have a river as the third boundary. There's your land. Looks beautiful. And these two roads meet at an 80-degree angle, which is easy enough to measure an angle where two things meet. Just need a protractor. Now, it's 230 feet on the longer road to the river and 150 feet on that shorter road. And we want to know the area of your land, which, of course, you need to know the area of your land so you know how much you're paying in taxes. So you can definitely measure this angle in here. It might be a little more difficult to measure this third side along the river. I mean, maybe you could. It's definitely pretty easy to measure the distance on the roads, but, I mean, who knows? Maybe there's some thick undergrowth or something along the river that makes it difficult to get your giant tape measure out and measure it. So for situations like this, the half-sine formula, 1/2 AB sine C, definitely works a lot better when you have that angle between the two sides. So just plugging things in here. Actually, I mean, pause the video and see if you can plug in the right things in the right places. All right, so for A and B, those are interchangeable. Doesn't really matter which is which. I'm going to use 150 for A, and for B, I'm going to use 230. For C, you have to use the angle between them, so this is going to be the sine of 80 degrees. And just like with using Heron's formula, I recommend you plug this whole thing into the calculator all at once without simplifying in between. So here I am on my calculator. I've plugged all that in, and that comes out to 16,987.9. And that is going to be in square feet since that's area. We'll do one more example problem. This is another real-life one. Let's say a painter needs to cover a triangular region with the following dimensions here, and a can of paint covers 40 square meters of area. How many cans to the next highest number of cans will we need? Pause the video and see if you can puzzle this one out. All right, so just like with the real-life SOHCAHTOA problems, this is a good one to draw a diagram for. So we've got a triangle, and we've got 35, 42, and 71, and this is not really drawn to scale even remotely, but it's a triangle with some numbers on it. So to figure out how many cans of paint we need, we first need to find the area of the original triangle. And then we could divide that by 40 to see how many cans of paint we have to use to cover that. So since we have all three sides given, this is where you had to make a decision now between Hero's formula and the half-sine formula. Three sides, side, 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 that's Heron's formula. So we start with our semi-perimeter with 1/2 A plus B plus C. So that's going to be 1/2, and we have 71 plus 35 plus 42, which I'll use the calculator for. So plugging those in, that all comes out to 74 even, which is nice. And now for the main part of the area formula. So here's that main formula again with the square root, the S minus A, S minus B, S minus C. So we've got the square root of 74, our semi-perimeter, times 74 minus 71, times 74 minus 35, times 74 minus 42. And let's just plug that into the calculator. So plugging all those in under one big square root, we end up with 526.4-ish, and that's square meters. But hold on a sec, the problem's not done. We wanted to know how many cans of paint we needed. So we need to divide this by 40 because it's 40 square meters that a can of paint covers. Let's see what that comes out to. So back on my calculator, since I've already got the answer that's the area, I'm just going to press the divide button, and that'll take my answer and divide it, and I'll just divide that by 40. Press enter, and that's 13.1 and some change, 13.2. But if you have this extra 0.159 of area of a can of a paint that you need to use, you can't just buy 0.159 of a can of paint. It's not that kind of store. You have to buy a whole extra can of paint to cover that little piece there. So we're going to round this up to 14 cans of paint. So at this point in the lesson, we're done with all of the how to do it kind of stuff, and you could just end now if you wanted to. But having said that, we've given you 2 magic formulas without any kind of proof where they come from. And if you are interested, feel free to stick around with this video and see a quick proof of the half-sine formula. And I'll at least give you a link to a proof of the Heron's formula. So here's half-sine. So half-sine situation, you've got 2 sides and an angle between them. Now, if we had the height of this non-right triangle, and I'll just draw a little h in here, if we had that h value, we could just use 1/2 base times height to find the height, or the area of this triangle. We don't have the height. We have A, we have B, we have C, angle C. So we need to express h in terms of sides and angles that we already have. So if you take a look at this, we do have a right triangle, which means we have access to all our right triangle tools, including SOHCAHTOA. If I wanted to find h, and I know this angle here and this side of this right triangle, what could I use to find h? Well, this is the angle opposite from h, and there is the hypotenuse, so that's going to be the sine function. So if you have an angle on another side, you can actually use sine to find this height. We could write sine of c equals opposite side h over a hypotenuse a, and then just rearranging this to get h by itself, multiplying by a, we see that h is actually the same as a times the sine of c. Okay, well that means we can replace the h in this formula up here with a times sine of c. So we could write 1/2 b times a sine c. But since we like to write things in alphabetical order, we instead write 1/2 ab sine c. But look what I highlighted in red here. The a and the b, or the a and the sine c, really are just this h value. So this is where that half-sine formula is coming from. It's just a modified version of the original area formula. Now, it turns out that using the area formula, the original area formula, and Pythagorean theorem, that is where Heron's formula comes from. It's a very long proof, but if you want to check out the proof, feel free to go to this link and peruse to your heart's content. So, until next time then, Mr. Sutton signing off.